Welcome back to the deep dive. The hour is definitely late, got the coffee going, and we're settling in to talk about some, well, truly spectacular, but also utterly terrifying near misses. Planetary history stuff.
Yeah, the big ones.
We're talking about the times complex life on Earth, nearly hit the ultimate reset button, like really close calls.
It's the perfect kind of topic for a late night deep dive, I think. We've been really digging into the research on this, exploring these moments when, well, the cosmos or the planet itself, or frankly, humanity,
Yeah.
decided to hold a knife right to our collective throat. So our mission tonight, basically, is to give you the full rundown, but, relaxed on just how fragile existence actually is.
Right. We're not trying to cause panic here. It's more about appreciating how often we've survived by the skin of our teeth. The sheer variety of threats is mind-boggling.
It really is. From deep, deep geological time, we're talking hundreds of millions of years ago,
Yeah.
all the way up to split-second technical failures in, 20th century bunkers.
Crazy. And what's fascinating, from our reading anyway, is that the knowledge we get from looking at these historical near extinctions, it actually tells us a lot about the existential threats we face right now.
Exactly. We're sort of connecting ancient history to the here and now. You see the patterns.
Okay, let's not bury the lead, though. We have to drop the hook, right away. Because some of the specific facts we dug up are just, well, they're wild.
Oh, absolutely. Get this. We're going to talk about the single human being, one guy.
Yeah.
Who back in 1983 was sitting in a Soviet bunker. His computer system starts screaming that U.S. missiles are incoming, full-on attack.
Oh, my God.
And he literally had to choose, follow protocol, launch the counterattack, or trust his gut feeling that it was a mistake, his skepticism, just his hunch.
Save the world.
Pretty much prevented global annihilation, billions of people.
No joke. Okay, they were going completely the other way, right?
Correct.
To the ultimate cosmic threat, this theoretical death ray.
A gamma ray burst, GRB.
Yeah, from a star collapsing thousands of light years away.
Yeah.
But it's so powerful it could completely strip away Earth's ozone layer.
Leaving us totally exposed to lethal radiation for years, just gone.
That's terrifying.
But, okay, before we even get to those near misses, the close calls, we have to start with the real deal, the genuine hard data catastrophe.
Right.
We're kicking off with the extinction event that wiped out 96% of all ocean life. 96%. The worst event in planetary history, period.
Forget the dinosaurs.
Forget the dinosaurs. This is the real great dying. And the chilling part, the mechanisms behind it they look terrifyingly familiar when you look at our current environmental trends.
Okay, let's dive into that first one then, the great dying. All right, let's unpack this first scenario, and it really is like the ultimate nightmare fuel. Happened about 252 million years ago?
Yeah, right at the boundary between the Permian and Triassic periods. And geologists, they don't call it the Great Dying lightly. The name's almost too gentle, for what actually went down.
Yeah, seems like an understatement.
So paint the picture for us. What was Earth like before this happened?
Okay, you got to appreciate the world that was lost, right? Permian Earth. It was a time of huge evolutionary success. We're talking the supercontinent Pangaea, massive, sprawling
landmass.
Basically, covered in these lush forests, lots of trees like Glossopteris, and the animals, complex fauna. You had the dominant synapsids, those early reptiles.
Like Dimetrodon, the one with the sail.
Exactly, Dimetrodon, spectacular creature, and lots of other mammal-like reptiles that were diversifying like crazy, a thriving, bustling, pretty stable planet for a long time.
It sounds idyllic almost. A robust ecosystem evolved over hundreds of millions of years, and then boom, Permian-Triassic boundary. Everything just stops.
That was hard.
What's the sheer finality here? Give us the scale of the destruction. We mentioned the number, but...
The scale is what makes it the deepest scar in Earth's history. It was pretty much a total biological reset. We lost, the estimates are 96% of all marine species.
96% in the ocean. And about 70% of terrestrial vertebrate species. So land animals with backbones. Think about that ocean number again. Out of every 100 species swimming or crawling around in the sea, only 4 made it through.
4% survival?
Yeah.
That's staggering.
Yeah.
It means entire branches of the tree of life just got chainsawed off.
Completely chainsawed off, yeah. Certain groups that had been super successful, dominated for millions, hundreds of millions of years, just vanished. Poof.
Haiku.
Trilobites. Gone forever. Rugose corals, these big reef builders, wiped clean. Blastoid echinoderms, sort of related to starfish, extinct.
Wow.
Their end wasn't slow and gradual. It was this sudden, violent, multi-pronged ecological collapse. And if you compare it to the KPG event, right? The one that got the non-avian dinosaur.
The asteroid one.
Yeah, that was quick, sure. An external shock. But it only killed about 75% of species, the Great Dying. It was slower, maybe 60,000 years for the main pulse, driven by internal Earth processes, and way more catastrophic in terms of sheer percentage killed.
And the recovery time. That's a terrifying measure of just how broken the planet got, isn't it?
Yeah.
Our readings suggest it took, what, 30 million years for ecosystems to really stabilize again?
30 million years!
Yeah.
That's just astonishing. It's more time than has passed since the dinosaurs died out.
Crazy.
It really speaks to the severity of the trauma. The entire structure of the food web was just shattered. The few survivors. There was this tough, burrowing reptile called Lystrosaurus.
Right, I read about that.
Yeah, it basically dominated the wasteland afterwards, sometimes making up like 90% of all vertebrate fossils you find from that immediate aftermath.
Just because it was tough.
Because it was a hardy generalist in a totally broken world. Not much else could survive.
Okay, so if it wasn't a giant space rock hitting us, and we'll get to those later, what was the culprit? What kind of geological weapon could trigger a collapse on this magnitude?
Well, the smoking gun points pretty directly at this. Colossal, sustained volcanic eruption, known as the Siberian Traps volcanism, modern-day Russia.
Traps, like stairs.
Yeah, from the Swedish word trappa for stairs, because the lava flows form these step-like hills. But we're not talking about a single volcano like Vesuvius or St. Helens. This was a flood basalt event.
Basalt.
Meaning the Earth's crust basically fractured over a huge area and magma just poured out continuously for maybe up to 1 million years.
When you say poured out,
Yeah.
you mean unimaginable scale.
Unimaginable is exactly the right word. This volcanic province, the area covered 2 million square kilometers. That's roughly the size of Western Europe or Australia.
Just covered in lava.
Covered in layers of lava that stacked up in places up to 6.5 kilometers thick.
Whoa.
Our research estimates the total volume of lava was around 4 million cubic kilometers.
Okay, near your comparison.
Right. Think about the Laki eruption in Iceland back in the 1780s. That caused crop failures across Europe, killed thousands from famine and pollution. The Siberian Traps dwarfed Laki by thousands of times. It was like a geological horror movie playing out in slow motion over millennia.
But the lava itself wasn't the main killer, was it?
Yeah.
It was what the volcanism erupted through and what it released into the atmosphere. That's what caused the global poisoning, right?
That's the critical detail, yes. The magma didn't just pour onto the surface. It erupted through thick layers of sedimentary rock underneath, stuff like coal seams, limestone, salt deposits, evaporates.
So it cooked them.
It literally cooked these massive deposits. And when you superheat those kinds of rocks, they release catastrophic amounts of toxic volatile compounds. Greenhouse gases were bad enough, CO2, methane, maybe up to 10,000 gigatons released.
10,000 gigatons, and that caused temperatures to spike.
Global temperatures probably jumped by 10 degrees Celsius, maybe more. Runaway global warming.
But you said toxic volatiles beyond the greenhouse gases. What else?
Exactly. The chemical attack was multi-pronged. First, huge amounts of sulfur dioxide. That leads to intense acid rain, which devastates plant life on land. That's why we see that weird 7 million year coal gap in the rock record after the extinction. No forests to make coal.
Okay. Acid rain, check. What else?
But perhaps the most insidious poison, nickel.
Nickel. Like it sounds random.
It's not random when you look at the chemistry. The magma itself was unusually rich in nickel. As this massive amount of volcanic material erupted and spread, it released high concentrations of nickel aerosols into the atmosphere, fine particles.
Okay, so nickel dust everywhere.
Which then dissolved into the oceans. And here's the twist. This massive influx of nickel acted like a super fertilizer for specific types of microbes in the ocean, particularly methanogens.
Methane-producing microbes?
Yep. These tiny organisms, suddenly swimming in nickel soup, went into overdrive. They started cranking out absolutely enormous quantities of hydrogen sulfide, HERO.
Which is bad.
Extremely toxic. Smells like rotten eggs, but much deadlier. It's poisonous to most complex life.
So you've got a geological process, the eruptions triggering a toxic microbial bloom in the oceans. That's terrifying.
Oh, it gets worse. Because this feeds directly into the cascade happening in the oceans. Remember the global warming?
10 degrees C warmer.
Warmer water holds less dissolved oxygen, so you start getting vast oceanic dead zones, anoxia, lack of oxygen.
Right.
And as the water becomes oxygen-free, it creates the perfect environment for other bacteria that produce hydrogen sulfide. So you get even more HEROs being produced in these anoxic zones. Models suggest maybe half the entire seafloor became oxygen-free.
Half the seafloor, so the deep oceans turn toxic, black, choked with this poisonous gas. And does it stay down there?
No, that's the nightmare scenario. As the surface waters warm up even more, that layer of toxic, anoxic, hydrogen sulfide-rich water starts to rise. It expands upwards. It essentially bubbles up and poisons the surface ecosystems too.
Oh, man. So there's nowhere to hide.
Pretty much. If you're marine life, you're simultaneously being cooked by the heat. Some estimates suggest shallow tropical waters might have hit 60 degrees Celsius.
60 C. That's like a hot tub from hell.
Right. You're being suffocated by the lack of oxygen, the anoxia, and poisoned by the rising hydrogen sulfide. And on top of all that, the excess CO2 dissolving in the water is causing ocean acidification.
Dissolving shells.
Dissolving the shells and skeletons of any marine life trying to hang on. Corals, mollusks. It was just a perfect storm of chemical and thermal trauma. A complete system collapse.
Wow. So the Permian extinction wasn't just one eruption. It was these feedback loops, right?
Yeah.
The warming triggered the anoxia fueled the toxic microbes, the nickel fed the other toxic microbes, the toxins and heat worsened the extinctions. The whole planet just kind of ate itself.
That's a good way to put it, yeah. And this is where we get that chilling aha moment, connecting this ancient catastrophe to our present day.
Because our reading draws some pretty direct, maybe unavoidable parallels, especially around the pace and the mechanisms of change.
Exactly. We established the Permian event was triggered by this massive release of greenhouse gases, right? CO2 and methane from the volcanoes cooking the rocks.
Okay, so where do we stand now with our own emissions?
Well, our current anthropogenic human-caused CO2 emissions are rising at a rate that, well, in some ways, it's comparable to, maybe even faster than, the rate of atmospheric change seen right before the Permian collapse.
Faster, really?
In terms of rate of injection, yes. If we continue on current trajectories, projections suggest we could approach maybe 20% of the total Permian greenhouse gas increase by the year 2100.
20% of a planet-killing dose in just a couple of centuries.
And critically, scientists are deeply concerned about triggering some of those same ancient feedback loops we just talked about.
You mean like the possibility of that methane thing, the clathrate gun hypothesis?
Exactly that. Methane clathrates, they're these ice-like solids that trap huge amounts of methane gas. They're found on continental slopes under the ocean floor, stable under high pressure and low temperature.
Okay.
The Permian warming likely destabilized vast amounts of these clathrates back then, releasing huge, rapid bursts of methane, which is a way more potent greenhouse gas than CO2, especially in the short term.
So warming releases methane. Methane causes more warming. Another feedback loop.
A potentially very dangerous one. If modern warming destabilizes our own huge clathrate reserves, we could experience a sudden, nonlinear jump in temperatures, something that accelerates the climate crisis far beyond our current, more linear predictions.
That is, terrifyingly relevant. And we're already seeing the distress signals from the oceans now, aren't we?
Yeah.
Mass coral bleaching.
Declining fish stocks. Those expanding oceanic dead zones.
It mirrors the Permian anoxia and acidification starting up.
It really does. And current extinction rates, they're estimated at maybe 100 to 1,000 times the normal background rate.
So the Great Dying is basically the ultimate cautionary tale written in stone.
It is. But here's the key difference, right? Unlike the poor synapsids of the Permian, who were just victims of unstoppable geological forces they couldn't possibly understand, we do understand the physics and chemistry. We know about greenhouse gases, feedback loops, tipping points.
We know the levers, whether they're volcanic or anthropogenic. We know what can trigger a biological reset.
We have agency, or at least the knowledge. The question is whether we use it.
Okay, let's leave the 250-million-year-old deep history for a bit. Rocket forward into the 20th century, we're moving to a completely different kind of threat now. A sudden, silent slap from the cosmos.
Yeah, no warning.
We're talking about the Tunguska event.
Yeah?
Siberia, June 30th, 1908. This one. It still feels like a proper mystery, doesn't it? Even though we basically know what happened.
Well, it's defined by what didn't happen, in a way. You have this massive flash in the sky, seen for hundreds of miles, a shockwave that registered on seismographs globally, an explosion estimated to be equivalent to maybe 3 to 5 megatons of TNT.
Which is like 1,000 times the Hiroshima bomb.
Easily. Huge power. And yet, Absolutely no crater.
Right. Just 80 million trees flattened outwards from a central point in this weird radial butterfly pattern. It's bizarre.
Yeah, the first investigators who got out there, like Leonid Kulik back in 1927, they were totally baffled.
Must have been a nightmare expedition.
Ugh, heroic effort. Facing extreme Siberian cold, terrible logistics, no real support, all because he was convinced he'd find this massive meteorite impact crater.
But there's nothing.
Nothing. He thought maybe the object, the meteorite, had buried itself in a swamp or something. But what he found instead was just this huge area, hundreds of square kilometers, of scorched, flattened forest, no hole.
So what cracked the puzzle? How did scientists figure out how you get that much destructive power without an actual impact crater?
It had to be an airburst. The scientific consensus now is pretty solid. It was a stony asteroid, not iron, maybe 50 to 80 meters across. Something like that.
So not enormous, but big enough.
Big enough. It entered the atmosphere at incredibly high velocity, and then it detonated, exploded, probably in an altitude of about 5 to 10 kilometers up.
Okay, why did it explode instead of hitting the ground?
Because it was stony, not dense iron. The immense atmospheric pressure and the incredible heat generated by plowing into the air at tens of thousands of kilometers per hour caused it to basically vaporize almost entirely before it could reach the surface. Ah, okay. So it wasn't the physical impact of the rock itself. It was the sudden, massive release of all its kinetic energy, its motion energy, way up in the atmosphere. The blast, not the bullet.
Exactly. That blast wave, that shock wave, propagated downwards and outwards, flattening everything beneath it in that characteristic pattern.
Which leads us to the really chilling hypothetical, right? The thing that keeps planetary defense people up at night.
Yeah. The location.
Yeah.
Pure luck. It happened over a very remote, sparsely populated region of Siberian forest.
But if it had happened just a few hours later...
Our reading really highlights this. The Earth rotates, right? If the timing had been just 4 or 5 hours different, the trajectory would have put that same 5-megaton airburst detonation directly over a major European city.
Like London.
Or London, St. Petersburg was the capital of Russia then, Paris, any of those densely populated areas.
Right. That would have changed history forever. Imagine the devastation. A major world capital just wiped off the map in 1908 by a 5-megaton blast from the sky. The loss of life would have been catastrophic. The collapse of governments, the global panic. I mean, you can't even really calculate the downstream effects. History absolutely hinged on just a few hours of cosmic timing. Dumb luck.
So Tunguska was basically humanity's first real cosmic wake-up call, wasn't it?
It was a slap in the face, yeah. It proved that these regional-level impact threats, while maybe rare, are inevitable. They will happen again. And critically, it spurred the realization eventually that we couldn't just sit back and wait. We needed active defense.
So fast forward to today. What does the modern response look like? How did we turn that near-miss lesson into, like, a functional planetary defense system?
Well, it took a while, but it led to the creation of dedicated organizations. NASA has its Planetary Defense Coordination Office, the PDCO. There are similar efforts internationally.
And their job is?
To actively monitor near-Earth objects, NEOs. Using networks of ground-based telescopes and space-based infrared telescopes like NEOWISE, they're cataloging tens of thousands of potential hazards.
Looking for the next Tunguska.
Looking for anything, really, but especially focusing on objects larger than about 140 meters across, because those are the ones that could cause truly catastrophic continent-level destruction if they hit.
So basically trying to map out the cosmic shooting gallery, predict the next incoming bullet. But just knowing it's coming isn't enough, right? We need the ability to actually do something about it.
Yeah.
Move the threat.
Exactly. Monitoring is step 1, deflection is step 2, and that's where the DART mission comes in.
Ah, yeah, the double asteroid redirection test. That was pretty cool.
Incredibly cool and successful. DART showed that humanity now actually possesses the technology to intervene. We can do it. By intentionally slamming a spacecraft, basically a smart metal box, into the small asteroid Dimorphos.
A kinetic impactor.
Right. We demonstrated that we can measurably alter the orbit of an asteroid. Just a tiny nudge.
And a tiny nudge. Given enough lead time, years or decades before potential impact is all you need, isn't it?
That's the beauty of orbital mechanics. A small change in velocity early on translates into a big change in position way down the line, enough for the Earth to just pass safely by where the impact would have been.
That's a genuinely magnificent piece of cooperative human ingenuity, isn't it? Born directly from the lesson of Tunguska that we live in a dangerous neighborhood.
And that cooperation part is absolutely key. While the threat remains, statistically, inevitable, Smaller objects like Tunguska will continue to hit maybe every century or a few centuries.
It's just a matter of time.
Our only real defense is robust, international, real-time monitoring, sharing data, and having agreed-upon deflection strategies ready to go if needed. We really are living on borrowed time, cosmically speaking. Collaboration is basically our planetary survival insurance policy. Midpoint break, listener engagement.
Hey, just going to jump in here real quick before we plunge back into it. And next up, we're talking geological beasts, specifically a supervolcano that literally hides under one of the most beautiful spots on Earth and could put the whole planet on ice. Trust me, this one is a real terrifying beauty.
Yeah, it's a big one.
If you are, digging this deep dive, seriously, we are a small channel trying to grow this thing, and we would absolutely love you on board. If you could take like 2 seconds, hit like, subscribe to the YouTube channel. It honestly helps us out a ton. Throw us a bone.
Yeah, every sub, it helps us find other curious, maybe slightly morbidly fascinated people.
Right.
Who enjoy contemplating the end of the world, but in a, intellectually rigorous way.
Exactly. Also, and we genuinely want to know, we're dying to hear what you think about these near misses so far. Seriously, what do you think? Comment below. Let us know which one gives you the biggest existential freakout.
Yeah.
Is it the total biological reset of the Permian? Or the split-second cosmic luck that saved London back in 1908?
We do read all the comments, and they genuinely help us figure out what rabbit holes to go down next.
Totally. Okay, back to it. Let's talk about a monster hiding in plain sight. Okay, so we've done ancient history, we've done outer space. Now let's bring it right back down to Earth, literally. Let's talk about a threat that is the actual centerpiece of a massively popular vacation spot, Yellowstone National Park.
Old Faithful, the geysers, the bison.
Yeah, all that postcard stuff. But
Yeah.
beneath it all, you got the Yellowstone supervolcano.
It really is the ultimate juxtaposition, isn't it? Serene natural beauty sitting right on top of terrifying geological power. The entire park basically is nestled inside the collapsed rim of a gigantic magma chamber. It's called a caldera.
And it's huge, right? Like how big?
The current caldera is about 30 by 35 miles across. That's massive. And it's an active supervolcano, which means its past eruptions absolutely dwarf anything modern humans have ever witnessed, like Vesuvius, Pinatubo, tiny in comparison.
So when we talk historical scale here, we're talking eruption events that reshape continents.
Pretty much. The geological record shows 3 really enormous caldera-forming eruptions from the spot over the last 2.1 million years or so.
3 big ones.
The largest was the first one, 2.1 million years ago, created something called the Huckleberry Ridge Tuff. But even the most recent major one, which formed the current caldera, that was the Lava Creek Tuff eruption about 630,000 years ago.
Okay.
That eruption blasted out an estimated 1,000 cubic kilometers of magma and ash.
1,000 cubic kilometers. That's insane. Mount St. Helens is like 1 cubic kilometer.
Exactly. So 1,000 times bigger than St. Helens. That volume is just staggering. It tells you Yellowstone isn't just a regular volcano. It's powered by a deep, persistent continental hotspot, a plume of extra hot mantle material rising from deep within the Earth.
Okay, but let's tackle the elephant in the room, right? The panic you sometimes hear that Yellowstone is overdue for another super eruption.
Yeah.
Because the big ones seem to happen every 600,000 to 800,000 years or so. And the last one was 630,000 years ago.
Right. That's the myth we really need to debunk, based on our reading of the geological science. While the record shows those 3 huge events in the past, volcanic recurrence, especially for supervolcanoes, is wildly unpredictable. It's not like clockwork.
So it's not due.
No. Geologists who study Yellowstone are very clear on this. The probability of another caldera-forming supereruption happening in any given year is incredibly low. The USGS puts it at less than 0.000014%.
Okay, that's tiny. Like ridiculously tiny odds.
Think of it like your odds of being hit by a civilization-ending asteroid this year. Possible, technically.
Yeah.
Likely, absolutely not. It's more likely you'd win the lottery, but, the prize is global catastrophe.
Right. And the good news is it's monitored constantly, isn't it?
What does the science tell us about its current state? Is it rumbling towards something big?
Our reading highlights that the magma reservoir beneath Yellowstone, while truly vast, it might hold up to 4,000 cubic kilometers of potentially eruptible material.
4,000.
Wow.
It's mostly not liquid magma. It's largely what they call a crystalline mush. Think of it like a giant underground blob of mostly solidified crystals with some liquid melt mixed in between them.
So it's not a giant underground lake of molten rock just waiting to burst. It's more like a giant, very hot slushy.
That's a pretty good analogy, yeah. A crystal-rich slushy. Estimates are that only about 6 to 8% of that whole reservoir is actually liquid melt right now.
Okay, only 6–8% melt. That sounds less scary.
It is, because for a super eruption to actually happen, you'd need a massive volume of that crystalline mush to rapidly remelt and gather together into one big, continuous, buoyant body of liquid magma. That takes an immense amount of time and a huge input of new heat from below.
And we're not seeing signs of that happening.
No. The current monitoring using seismographs to track earthquakes, GPS to measure ground deformation, gas sensors, thermal imaging, it shows no signs of that kind of massive melt accumulation happening. We see regular, localized ground uplift and sinking, lots of small earthquake swarms.
Which sounds alarming.
It's actually normal for an active volcanic and hydrothermal system like Yellowstone. It's the volcano breathing, basically.
Yep.
But there's absolutely no indication of an imminent super eruption.
Okay, that definitely gives us some breathing room, puts the yearly panic into perspective. But we still have to explore the what if, right? For the sake of understanding the potential threat. If that incredibly unlikely event did happen, what's the sequence of global disaster look like?
Right. If Yellowstone were to have another caldera-forming eruption, the immediate regional devastation would be, well, absolute. Pyroclastic flows. These superheated clouds of ash and gas moving at hundreds of miles per hour would incinerate everything for maybe 100 miles around. Massive earthquakes. And then the ash fall, feet deep across Montana, Idaho, Wyoming. Total obliteration of the immediate area.
Okay, horrific regionally.
Yeah.
But the real consequence, the global one, that comes from the ash that gets thrown way up high, right, blocking the sun.
Exactly. We're talking about a genuine global winter scenario, possibly lasting for years.
How does that work?
A supereruption would inject enormous quantities of volcanic ash and, critically, sulfur dioxide gas high into the stratosphere, way above the weather. These tiny particles, especially the sulfate aerosols formed from the gas, circulate globally. They act like tiny mirrors,
Reflecting sunlight back into space.
dramatically increasing the Earth's albedo, its reflectivity. Less sunlight reaches the surface, leading to significant prolonged global cooling, maybe several degrees Celsius drop in average global temperature, lasting for years.
And the immediate effect of that is?
Guaranteed worldwide crop failures, especially devastating across the major agricultural breadbaskets of the Northern Hemisphere, North America, Europe, Asia. Widespread famine becomes a very real possibility.
So we move instantly from a localized geological disaster in the U.S. West to an immediate global food security crisis. And infrastructure collapse too, right? Ash is nasty stuff.
Oh, yeah. Volcanic ash is basically tiny shards of sharp rock and glass. It's incredibly abrasive, it's heavy when wet, it's corrosive, it's conductive when moist.
So it screws up everything.
Pretty much. It would shut down power grids. Ash accumulation causes short circuits on insulators and can collapse transmission lines. It jams up mechanical systems, engines, filters. All air travel would halt globally, probably for months or years. Ground transportation becomes incredibly difficult, if not impossible, in vast regions covered by thick ash. Electronic systems could fail. Our complex, just-in-time global supply chains would shatter instantly. Mass scarcity hits immediately.
And that triggers societal breakdown, doesn't it?
You'd have to assume so. Borders would likely slam shut as nations try to hoard resources. You could see mass migrations out of the coldest, hardest-hit, starving regions, probably heading towards the equator. It could lead to a desperate global scramble for dwindling food and fuel supplies. Conflict seems almost inevitable in a world suddenly draped in volcanic twilight for years on end.
Man, it really shifts survival back to basics, doesn't it? Less about high technology, more about simple agrarian resilience and just enduring.
It would be a profound test of the human spirit, absolutely, to endure years of persistent global cooling, darkness, and widespread food insecurity.
So, back to the monitoring for a second.
Yeah.
How reliable is it? If that crystal mush did start to rapidly melt and accumulate, how much warning would we actually get before the big one blew?
That's a critical question. The scientists monitoring Yellowstone use a whole suite of tools, as we said. Seismographs catching earthquake swarms as magma moves, GPS tracking ground uplift millimeter by millimeter as pressure builds, gas measurements, thermal imaging.
Okay.
Our readings suggest that the really strong precursors, things like rapidly accelerating ground deformation over a wide area, intense earthquake swarms unlike the normal background activity, huge spikes in gas emissions like sulfur dioxide, those might only provide weeks, maybe months of warning before an eruption of that magnitude actually begins.
That's a month. That's not a lot of time.
It would likely be enough time to evacuate the immediate region, saving potentially millions of lives in the direct blast zone. But it's almost certainly not enough time to prepare the global agricultural system or a critical infrastructure for the years of volcanic winter that would follow.
So we'd likely know what was coming, maybe shortly before. But the global consequences, those would be largely unavoidable. The recovery, again, would rely heavily on human ingenuity, resourcefulness, and sheer luck that society doesn't completely collapse into chaos during those long, cold years.
Pretty much. It's a sobering thought hiding under such a beautiful park.
All right, let's pivot again. We've gone from the geological beast literally beneath our feet. Now let's look way, way out to the ultimate abstract terror, maybe, lurking in the vastness of space. We need to talk about gamma ray bursts, GRBs.
Yeah, this is the threat that really makes you appreciate the sheer scale and violence of the universe and maybe the protective bubble of empty space around us.
So what are they? What causes them?
Okay, GRBs are, hands down, the most energetic, most powerful, explosive events in the entire universe since the Big Bang itself. They come from truly cataclysmic cosmic events. There are basically two main types we know of.
Okay.
You have short GRBs, lasting maybe less than 2 seconds, sometimes just milliseconds. Those are thought to come from the merger of two incredibly dense objects, like two neutron stars colliding, or maybe a neutron star and a black hole.
Neutron-star collision.
Got it.
And the other type?
Long GRBs. These can last from a few seconds up to several minutes. These are believed to happen when a truly massive star, maybe dozens of times the mass of our sun, reaches the end of its life. Its core collapses catastrophically, directly forming a black hole, and in the process, launching these incredibly powerful jets. It's called a hypernova or collapsar event.
Okay, hypernova. The sheer physics of the energy release here. It's hard to even wrap your head around, right?
It really is. A single GRB, in just those few seconds or minutes it's active, can release more focus energy than our sun will emit over its entire 10 billion year lifespan.
More energy than the sun's entire life. In seconds. That's ridiculous. An instantaneous cosmic flashbulb of unimaginable power.
Right. And crucially, that power isn't usually radiated outwards equally in all directions like a normal supernova. It's channeled, concentrated into two incredibly tight, focused beams, relativistic jets, they call them. Particles accelerated to near the speed of light, shooting out from the poles of the collapsing star or the merging neutron stars.
Like lighthouse booms.
Exactly like lighthouse beams. And that's what makes it a genuine cosmic death ray. The danger isn't just that a GRB happens somewhere out there. The danger is the orientation of those beams. Is one pointed at us?
So the GRB itself could be happening thousands of light years away, which sounds incredibly far. But if one of those focused beams happens to sweep across Earth as it travels through space, it could still be lethal.
Absolutely lethal. The potential danger zone is staggering. Our reading suggests that if a long GRB were to happen within, say, a few thousand light years of Earth, which is relatively close in galactic terms, and if that focus beam happened to be aimed directly at us, it presents a genuine extinction-level event.
And there's nothing we could do, right?
No.
We can't deflect gamma rays. We can't stop it.
Nothing. We just have to be lucky. Lucky that the universe's most powerful explosions aren't pointed our way very often.
That's horrifying because, well, it's a threat we can potentially monitor. We can detect GRBs happening all the time in distant galaxies, but we have zero defense against it. And it travels at the speed of light, right?
Yeah.
So there's no warning.
Exactly. We would know we were hit the instant the radiation arrived. No lead time.
So what's the kill mechanism? It's not like the gamma rays themselves would instantly, cook the surface of the Earth from thousands of light years away, would they?
No, not directly incinerate. It's more insidious than that. It's what the initial burst of gamma rays does to our upper atmosphere. They effectively strip away Earth's primary defense system against deadly radiation from space, the ozone layer.
Ozone annihilation. Okay, walk us through that chemical breakdown, because that's the really nasty part, isn't it?
It is. When those incredibly high-energy gamma-ray photons slam into the top of our atmosphere, they collide with nitrogen and oxygen molecules, N22 and OD2. This collision creates a shower, a cascade of secondary particles. Critically, these reactions produce huge quantities of nitrogen oxides, various molecules like Nutridol or NO2, usually just written as NOx.
Nitrogen oxides, okay. And those are bad for ozone.
They are incredibly efficient catalysts for ozone or O33 destruction. They don't just temporarily damage the ozone layer, they actively chew it up, breaking ozone molecules back down into regular oxygen.
So they act like little Pac-Men, just eating the ozone.
A very effective analogy, yeah. And they don't get used up in the reaction, so a single NOSM molecule can destroy thousands of ozone molecules. The initial gamma ray burst might only last for seconds or minutes, but the nitrogen oxides it creates high in the stratosphere can persist up there for years.
For years, wow.
Yeah, so the result is that the entire ozone layer, our shield that protects surface life from the sun's harmful ultraviolet UV radiation, could be severely depleted, maybe almost entirely stripped away globally.
And that exposure to intense UV radiation,
Yeah.
that's the killer.
That's the killer. Suddenly, all life on the surface, and even in the upper layers of the ocean, is bathed in lethal levels of UVB and UVC radiation. This would last for perhaps half a decade, maybe longer, until the atmospheric chemistry can slowly regenerate the ozone layer naturally.
And what does that do to ecosystems?
It would be catastrophic, especially for the base of the food chain. Phytoplankton in the oceans, which are already sensitive to UV light, would crash hard. Terrestrial plants would suffer massive DNA damage, mutations, reduced photosynthesis. Animals would suffer severe sunburns, cataracts, immune system suppression, cancers. Ecosystems would likely collapse from the bottom up.
Has this ever happened? Have scientists looked for evidence of a past GRB hit in the geological record?
They have, yes. There's been active searching for a potential GRB footprint linked to past mass extinctions. The leading hypothesis, though still debated, links a possible GRB event to the Ordovician Silurian extinction, which happened about 440 million years ago.
The Ordovician, what happened then?
It was one of the big five mass extinctions. About 85% of all species were lost, predominantly marine life living in shallow seas, which fits the profile of ozone depletion letting in deadly UV.
Okay, so why is the evidence still elusive or debated? If it happened, shouldn't there be a clear sign?
It's tricky because the direct chemical signature, the nitrogen oxides, wouldn't last 440 million years. What researchers look for are more subtle indirect traces. Things like fossil spores from that period that show evidence of unusually high mutation rates or deformities consistent with extreme UV exposure, or specific isotope changes in sediments. The physics definitely supports the threat as plausible, but finding that definitive, undeniable geological smoking gun proving a GRB caused the Ordovician extinction is extremely challenging.
So we basically exist here partly due to cosmic luck, because the universe's most powerful weapons just haven't happened to be pointed directly at our little corner of the galaxy recently.
That's a big part of it, yeah. It definitely deepens your appreciation for the cosmic luck, the sheer chance involved in life persisting on any planet in such a potentially violent universe.
And it makes you value that ozone layer a little more.
Absolutely. So we monitor the skies with gamma-ray telescopes, not just to track local asteroids, but also to understand our place relative to these incredibly distant yet potentially existential stellar events.
Okay, wow. We have spent this deep dive looking at these enormous, almost impersonal existential threats, right? From the deep Earth, from the cosmos, forces we really can't control. Now we have to transition. We have to talk about maybe the most unnerving threat of all.
The one we made ourselves.
Exactly. The one that highlights the incredible, catastrophic fallibility of human design, human systems, and human decision-making under pressure. We're moving into the era of anthropogenic peril. The Cold War near misses. Nuclear annihilation.
The transition is pretty stark, isn't it? We go from billions of years of geological time, millions of light years of space, down to the critical space inside a human brain, and a few incredibly tense minutes inside a concrete bunker somewhere.
Yeah.
This is the existential threat we literally built with our own hands. The whole precarious situation was perfectly symbolized for decades by the Bulletin of the Atomic Scientist's Doomsday Clock, right? That constant, stark reflection of how close we set ourselves to midnight.
And the ultimate stress test for that system, the time it came closest to failing completely, was the Cuban Missile Crisis, October 1962. 13 days where the entire world genuinely held its breath.
Yeah.
We all know the basic story, right? Soviet missiles secretly deployed to Cuba, JFK imposing the naval quarantine, the blockade, the tense negotiations. But our reading, especially looking at the declassified accounts now, it reveals just how chaotic things were on the ground and the microscopic margins of error involved.
Oh, absolutely. The historical accounts show just how terrifyingly close both sides came to escalating beyond diplomacy, sometimes due to accidents or misinterpretations. But perhaps the single sketchiest moment, the one that relies purely on one person's judgment call, involves a Soviet submarine, the B-59 down in the Caribbean.
Okay, tell us about B-59. That story it's pure cinematic terror when you read about it.
Right, so the U.S. Navy is enforcing the blockade. They're dropping these small, non-lethal practice depth charges near Soviet submarines they detect, trying to signal them to surface and identify themselves. Not intended as an attack.
Okay, practice depth charges.
But down inside submarine B-59, they are completely cut off from radio contact with Moscow. Conditions are apparently hellish extreme heat, high CO2 levels, crew exhausted and stressed. They hear these explosions going off around their hull.
And they think.
They think they're under actual attack. They assume World War III has already started up on the surface.
Oh, God. And the B-59 wasn't just any sub, was it? It was armed with something special.
It was armed with a nuclear-tipped torpedo, with a yield reportedly similar to the Hiroshima bomb.
Jesus. Okay, so they think they're under attack, and they have a nuke. What stops them from using it?
Soviet protocol at the time apparently required 3 senior officers on board, the captain, the political officer, and the flotilla commander, who happened to be on board, Vasily Arkhipov, to unanimously agree to launch a nuclear weapon.
3 yes votes needed.
Right. And the submarine captain, Savitsky, and the political officer, they were both convinced war had begun. They were ready to fire the nuclear torpedo, believing they were acting in self-defense, or maybe even preempting a deeper attack.
So 2 out of 3 votes were yes. It all came down to the third guy, Arkhipov.
Vasily Arkhipov. And Arkhipov, despite the chaos, the heat, the stress, the explosions, he apparently kept a cooler head. He argued against launching. He doubted they were really at war. He insisted they should surface the submarine first, reestablish contact with Moscow, and confirm the situation before unleashing a nuclear weapon that would have guaranteed an immediate, full-scale nuclear retaliation from the U.S.
Wow. One man's sanity. His institutional skepticism, maybe. Not just following the we're under attack assumption.
His refusal to launch, based on his own judgment against the apparent evidence and the pressure from the other officers, it almost certainly prevented World War III from starting right there in the Caribbean Sea. One man.
That's astonishing. Truly astonishing. But Arkhipov wasn't the only quiet hero, was he? Working against technical error or faulty intelligence during the Cold War? This brings us to Stanislav Petrov, the man who, in 1983, literally saved billions based purely on a gut feeling.
Yeah, the Petrov incident, September 1983. This is maybe the absolute peak example of the terrifying intersection between machine error and human judgment. Petrov was the lieutenant colonel on duty at Serpukhov 15, the Soviet early warning command center just outside Moscow.
Okay, and what happened?
His brand new satellite warning system suddenly, out of the blue, flags an incoming missile launch from the United States, then another, up to 5 ICBMs apparently headed towards the Soviet Union.
The computer system, the most sophisticated technology they had, designed for exactly this purpose, screaming, "Attack underway, nuclear missiles incoming, retaliate now."
Sirens blaring, lights flashing, screens showing multiple missile tracks. The system reported 5 Minuteman ICBMs inbound. Petrov's direct operational protocol was crystal clear. Immediately report this detection up the chain of command as a confirmed attack.
Which would have triggered.
Which would almost certainly have led to Soviet leadership ordering a massive retaliatory nuclear launch against the U.S. and its NATO allies, based on the assumption they were under a decapitating first strike. Mutually assured destruction in action.
But Petrov, he hesitated. He didn't make the call immediately.
He hesitated. He had maybe minutes to decide whether to pass the alert up or declare it a false alarm.
Why? Why did he hesitate? What was the internal calculation, the logic that allowed him to potentially defy the machine, defy his orders?
His reasoning, according to his own accounts later, was pure human skepticism and logical deduction. He thought about it. If the United States was really launching a surprise nuclear first strike, would they only launch 5 missiles?
No way.
No way. They would unleash everything. Hundreds, thousands of warheads to try and guarantee the annihilation of Soviet retaliatory capabilities. 5 missiles seemed, well, it seemed illogical as a first strike. It didn't make sense militarily.
So his gut told him it was wrong.
He concluded it had to be a system malfunction, a computer glitch. He trusted his intuition, his understanding of military doctrine, over the absolute certainty being presented by the flashing screens and warning klaxons.
And he was right, wasn't he?
He was absolutely right. It was later determined to be a freak occurrence sunlight reflecting off high-altitude clouds near the horizon at just the right angle to be misinterpreted by the satellite's infrared sensors as the heat bloom of multiple missile launches, a flaw in the software logic.
Wow. Wow. So he reported it as a false alarm against protocol.
He reported it as a system malfunction, yeah. He risked enormous professional disgrace, maybe even prison or worse for dereliction of duty if he'd been wrong, but he stuck to his guns. One man's cool, logical skepticism saved the world from potential nuclear holocaust. It's absolutely nuts to think about how close we came because of sunlight hitting clouds. And 1983, that whole year was incredibly perilous, maybe the most dangerous since the Cuban Missile Crisis itself. Because earlier that same year, there was another major incident involving misinterpretation.
Right, the NATO exercise, Able Archer 83.
Yeah, Able Archer 83. This was a large-scale NATO command post exercise held in November 1983. It was designed to simulate the full process of transitioning from conventional warfare in Europe to a general nuclear release.
Okay, a simulation. But the Soviets didn't see it that way.
Soviet intelligence, already deeply paranoid about a potential surprise nuclear attack from Reagan's administration. Remember the evil empire rhetoric, the SDI Star Wars program announcement? They genuinely misinterpreted the realism of the Able Archer exercise.
How so?
Because the exercise involved unusually realistic elements. They used new encrypted communication systems, simulated nuclear warhead release procedures using actual codes, involved heads of government like Thatcher and Kohl moving to secure command bunkers, to the KGB and Soviet military intelligence who were monitoring all this. It looked terrifyingly like the real thing, like the exercise was actually a cover for launching a genuine first strike.
So they thought Able Archer was the start of World War III.
They were apparently convinced it might be. Soviet nuclear forces in East Germany and Poland were reportedly placed on high alert. Fighters were armed with nuclear bombs ready for immediate takeoff. The world was, once again, teetering on the brink, driven there by profound miscommunication, mistrust, and paranoia, amplified by the realism of a military drill.
Man. So we had a confluence of near disasters just in 1983 alone. A terrifying technological glitch caught only by one man's gut feeling, Petrov, and a massive failure of communication and interpretation leading to near panic on both sides, Able Archer. All completely self-inflicted wounds.
Absolutely. And the major takeaway, I think, from the entire Cold War period is that the most acute, the most immediate existential threat we often face isn't necessarily from space or geology. It lies within our own complex systems, both human and technical, especially when they're put under extreme stress.
And even though the specific Cold War superpower standoff is over, those underlying risks haven't entirely vanished, have they?
No. Nuclear proliferation continues. Regional tensions exist. The potential for cyber attacks on command and control systems is a new nightmare. And the basic chance of technical malfunction, or human error, or a catastrophic failure of judgment under pressure, that remains perhaps the single greatest, immediately preventable existential threat we face.
Yeah. We can't stop a GRB beam from hitting us. We can't stop Yellowstone from eventually building up heat again over millennia. But we absolutely can implement better safeguards, maintain clear communication channels like the hotline, build de-escalation protocols. We can stop us from destroying us. Hopefully. Man. Okay. We have covered some serious ground tonight, haven't we? We went from 250 million years ago, watching life get absolutely hammered by volcanic poison gas,
So they dying. Yeah.
to witnessing the cosmic slap of Tunguska, that wake-up call from space. We peered into the beautiful, terrifying heart of the Yellowstone supervolcano.
Hiding in plain sight.
We dodged a theoretical death ray from a collapsing star halfway across the galaxy. And then, maybe most chillingly, we relied on the quick wits and sheer luck of a Soviet submarine officer and a duty officer staring at a faulty computer screen to prevent self-inflicted nuclear apocalypse.
It's quite a list. And if you sort of synthesize all 5 of those threats, the themes that emerge are pretty stark, aren't they? On the one hand, life is incredibly resilient. It bounced back even from that 96% loss at the Permian boundary, given enough time.
Right.
But it's also desperately, terrifyingly fragile, saved repeatedly, as we saw, by sheer cosmic luck. The Tunguska impact angle, the GRB beam missing us, or almost more unnervingly, saved by the judgment call of a single individual defying protocol under immense pressure.
Yeah. And connecting all this knowledge back to you, listening right now, we've seen that the ancient synapsids, the trilobites, they were just victims of a planetary cosmic disaster they could never possibly comprehend, let alone prevent.
Right. But humanity, we're different. We have agency. We understand the mechanisms of climate collapse now, even if we argue about the solutions. We track the asteroids. We know how easily technical glitches or misinterpretations can escalate to global catastrophe. That knowledge, that understanding, it's our only real advantage. It's what separates us from just being passive victims of the next inevitable crisis.
It shifts the perspective, doesn't it? From just, like, waiting for doom to realizing we have a role in actively managing risk, and maybe just appreciating the incredibly delicate balance required for complex civilization to survive on this often volatile planet, in this often violent universe.
Well said.
So, okay, let's leave you with a final thought tonight, something to maybe mull over as you drift off,
Yeah.
or maybe keep you up for another 5 minutes.
Building on our reading, but taking it a step further, consider the Permian extinction again, the Great Dying. We establish it has some unnerving parallels to current anthropogenic climate trends, right, in terms of the speed and drivers of change.
Mm-hmm.
And we know it took a staggering 30 million years for complex life, for biodiversity to truly recover its previous levels after that event. So the question to ponder is, if our current trajectory continues to mirror some aspects of that ancient collapse, how long will it actually take for the Earth's biosphere to recover from humanity's impact? Even if we manage to somehow navigate the challenges we've created and survive as a species, what's the recovery timescale for the planet itself?
Oof, 30 million years is a long time to wait for the coral reefs to come back. And maybe one more thing to chew on is that human tendency we saw for the dramatic near miss. Our apparent reliance on a single person's skeptical judgment, like Petrov's decision or Arkhipav's refusal in the sub, is that a sustainable long-term strategy for planetary survival? Can we keep getting lucky? Can we keep relying on pure split-second individual heroism or intuition to pull us back from the brink?
Or do we need to fundamentally redesign our global systems, technological, political, economic, to be inherently more robust? To eliminate those single points of catastrophic failure in the first place, can we build systems that don't put the fate of billions in the hands of one stressed person staring at a screen?
Heavy thoughts. Think about the fragility. Think about the resilience. And think about the power and maybe the burden of individual choice and collective action.
Thank you for joining us for this deep dive into Earth's near misses.
Yeah, thanks for hanging out late with us. Sleep tight, hopefully. I'll catch you on the next one.